So in part 2 of section 4.1, we're going to start looking at linear applications or applications of linear functions. So in example 4, they talk about the monthly cost in dollars if a certain cellular phone plan is given by the function c of x is equal to 0.38 x plus 5. And they tell us where x is the number of minutes used. So I'm just going to write down over here just so I know what my variables are. So x is the number of minutes. And then c is the cost of those minutes. So it's going to be in terms of dollars. So that helps me keep track of the units. Part A is asking us, what is the cost if you talk on the phone for 50 minutes? So we're recognizing that X is those 50 minutes. And again, I know that for a couple reasons, because it's the input value and they labeled it in terms of minutes. So I know it's my input value. So we simply are plugging 50 into our function. We're going to find C of 50. That would be 0.38 times 50. And then we'll add 5. So 0.38 times 50 comes out to be 19. Plus 5 gives us $24. So if you talk on this phone for 50 minutes, they're going to cost you $24. And I realize that cell plans don't do this anymore, but it's a really nice place to start with those linear applications. Part B on that problem says, suppose your monthly bill is $29.32. So they're giving me the cost. They want to know how many minutes we're going to use the phone for. Well, they gave me the cost. So they gave me the output, and we need to solve for the input. So 29.32 is equal to 0.38x plus the 5. So we're going to move the 5 over. That'll give me 24.32 when I subtract it, equals 0.38x. Then we'll divide out the 0.38x. So x comes out to be equal to 64 minutes. So if you talk on the phone for 64 minutes, this certain plan will cost you $29.32 a month. Finally, part C on that problem says, suppose that you budget $60 a month for the phone. That's it. That's all you get. What's the maximum number of minutes you can talk? So again, because the 60 is in terms of dollars, I know that that's the output. We're going to put it in for the output C of x and solve for x again. So we'll get 55 is equal to 0.38x when we move the 5. And then dividing out the 0.38 is going to give us, when you plug it into the calculator, you get 144.7. And now we need to talk about how to round this. Do I want to round it, or do I want to truncate it? So rounding it would knock it up to 145. However, if you plug the 145 back in, you're going to see that this cost is more than $60. Not by much, right? But it is more than the $60. So for once we're going to truncate it, we don't do that very often. We're going to call it 144 cents. Again, if you use more than 144, you've gone over your budgeted $60. So moving on to example 2. Example 2 comes from the economic world with supply and demand equations. Some of you will go on and take an economics course. This is example 5, sorry, not example 2. The second application example, but it's example 5. Suppose that the quantity supplied S and the quantity demanded hot dogs at a baseball game are given by the following functions. So I have S of P, which is equal to a negative 2,000 plus 3,000 P, and I have D of P, which is equal to 10,000 minus 1,000 P. So again, S stands for supply, D stands for demand. And just so we have it, keeping track of what these variables are. So P is going to be the price of the hot dog when we're all done, price of hot dog. And then the output is going to be the number of hot dogs. I can spell. I don't know what an out dog is. Hot dogs. Okay, there we go. So, and I didn't label this with one of the specific functions because both of these you input the price and you'll get out of it the number of hot dogs. Here, you put in the price, you get the supply of the hot dogs. Here, if you put in the price, you get the demand for the hot dogs. Now, they're not asking us to graph it, but I think the graph gives us an idea of what's going on. So, this would be price, and this is quantity. And we're not going to do a really careful graph. What we are going to notice is that for the supply equation, it has a positive slope. That's that positive 3,000 P, so it's going up. So there's your supply equation. Now the demand equation has a negative slope, so it's going to go down. So these two are going to meet someplace, and the place where they meet is called the equilibrium point. Equilibrium point. So it's the place where the actual number of hot dogs that we bring to the game to sell is going to actually get sold. We won't have any leftovers. We won't have a demand for more of them. That's the equilibrium point. And that's where supply and demand are equal to each other. So there's our background. Part A is asking us, they want to know, find the equilibrium price for the hot dogs at the baseball game. And what's the equilibrium quantity? They're asking me to find that equilibrium point. So we need the point of intersection. Well, the point of intersection is where these two guys are going to cross, and they're going to cross when they're equal to each other. So we're simply going to take the 2,000 plus 3,000 P and set it equal to the 10,000 minus 1,000 P. And we'll solve for P. So again, what we're doing is we're setting S equal to D. So D. Okay, well, I'm going to move the P's to the left side. That'll give me 4,000. And then I'm going to move the negative 2,000 to the right side, giving me 12,000. And then we'll divide out the 4,000. So P comes out to be 3. So what is that? Again, P is the price. So that's the equilibrium price. So I'm going to sell the hot dogs for $3 each. If I do that, I'll sell all of the hot dogs I brought or I have available. So we need to figure out how many that is. We're going to take that 3, and you can plug it into either of the equations, the supply equation or the demand equation. It's not going to matter. I'm going to go for D of P. So D of 3 would be 10,000 minus 1,000 times 3. That's 10,000 minus 3,000, which is 7,000 hot dogs. So the equilibrium price is $3. The equilibrium quantity is 7,000 hot dogs. So it works out really quick. And again, you can plug the 3 into this one. Plug it into this one, you get negative 2,000 plus 9,000, which is again 7,000. Part B on that problem is going to come back and make use of that picture. So they want to know, determine the prices for which the quantity demanded is less than the quantity supplied. So where is the demand less than the supply? Well, this is similar to the one we worked before we started the application problems. It's a picture, and they're asking me for when the D function, that's this guy, is less than the S function. Well, we already know that this is at $3 and 7,000. So we know that the demand is going to be less than the supply anytime you're larger than $3. So we're going to say whenever P is greater than 3. So you could come in and put the inequality statement in here. Make sure you get it pointed in the right direction. We want the demand to be less than the supply. So you want the supply to be bigger than the demand, because this is S on this side and D on this side. So notice that it points towards D, it's pointing towards D. So you can come back in and walk that inequality through, and you're going to see that the price comes out to be greater than $3. So, but the graph was a quicker way to do it. It really was. So